Okay, my friends, this is going to be interesting. This is Roger, the fairest fair user in the land, and that's what I am doing, the Fair Use Act. This is from the Royal Institution in London, and I think they might block me for copyright stuff, but I am allowed to comment on copyrighted things without any permissions whatsoever, because I am doing it for transformational purposes, educational purposes. And I am going to explain the particles that they're talking about looking for at CERN. Now, I'm just going to let this play, and then I'm going to explain what they are looking for.
Well, we discovered the Higgs boson, which was the last missing piece in the Standard Model. The Standard Model is this theoretical framework that we have now to explain what matter is made of. And it's very successful, and it has answered thousands of questions. But the problem is that now we know that there are questions that are not addressed by the Standard Model, and we need to find something else. The big question is, what is it? So at this point, we're absolutely stuck for two reasons. Theorists have tons of ideas, but we cannot sort out which one is good until we find new particles that would put us on the right track. But the problem is that experimental physicists like myself, we haven't found anything in the last 10 years. So we're really at a difficult point right now, because we know that we need to find something else, because what we have is incomplete and flawed. So,
okay, let's show you what is complete and not flawed. Okay, this is pulsed red laser, and these little particles that are in front of the wave are the particles that are being concussed. There's a particle in here as well. It has a magnetic field around it that creates the wave. Now here we are accelerating the particle out of the wave, and then it's stacking up on itself at the venturi, which is a little device that crushes the fields. It's an accelerator. The way that they rate accelerators is by the luminosity they create, and that there is nothing more luminous than that. That's as luminous as it gets. These are actually particles that are in the air that are unseen because they're not concussing enough. Well, now they're concussing very brightly because of the reverse push from this literal explosion. Now, these are our Higgs fields. They talk about Higgs fields. There's a particle nobody's ever seen before, and that's the only one I've ever seen of it. Now, this is the particle manifesting itself, and I'll show you all three flavors of neutrinos, because this solves everything. Everything is a dipole. Here's my claim. Instead of a proton being like this with a couple of little quarks or whatever in there, it is nothing more than a whole batch of electrons, and every electron is a dipole. It's a little magnet. It's a little bar magnet, and I'll show you this. Watch, click, click, and then when they hit a certain frequency, a certain quantity, they become stable. Hydrogen is about 1835 or so, which is one atomic mass unit. So instead of this being hydrogen's nucleus, this is hydrogen's nucleus. And one more electron wants to get in, but there's enough electron pushing back, because they push, the whites push, the blacks don't. And you don't see it yet, but we will in a second. I'll show you how these develop. That's what creates the particles are nothing more than electrons going through the air, back to back, make photons. I'll show you that right now. All right, there's your gravity and dark matter. They have seen this. It's called a muon, and it's just one size fits all, black, heavy-duty particle. These are glowy little, and they have very, very little, almost no mass at all. And here they are as photons. Each one of these is just like a bar magnet, has a positive and a negative, positive and a negative. Back to back, they make a photon. This is this particle. This just shows their energetic values. So don't forget, they've seen these. They have no question about they see them. But the problem is with CERN and Fermilab and all the other accelerators is they're using protons. Protons are these gigantic particles, gigantic compared to us. We're using this. We're just using something like that. All right? And they come through the air and then they show up as these particles just before they separate. It's right here that they start to show up. Now, and I'm going to show you them actually turning into the neutrinos, because I'm going to tell you right now, that is an electron neutrino, and that is a muon neutrino. Stuck together, they are electrons. They call them gluons. One gluon and another one back to back is a photon. That's what these are, photons. Now, what happens to photons? Well, they're light. Guess what? We can separate that light and we can accelerate that light. Here was that particle right back here. It's accelerating and it's stacking up right here. And then at the venturi, it actually separates the black from the white. You see the black and the white separate? And they come back together here. Here they separate. Here they come back together. This is nothing more than a venturi. Just like that. And it has to force these fields to crush each other. Muon neutrino is the black ball. Does not change. That's the black ball separated from the white. And the white electron neutrino turns into the shower. There's the shower. We work with light, and that's what they want to do, but they never could figure out how to do it. All you have to do is focus the light down through the venturi and construct it correctly, and you get this kind of acceleration, which is, and like I said, they rate particle accelerators on their luminosity. You can't get any more luminous than this. Let me show you this, how reverse. It's just unbelievable how explosive that particle has become. I want you to know the green is the same. You see that green particle? The green and the black? This one's just getting ready to flip. It's getting overcharged, the one that's forward. And it will flip, and then that one will come forward. Now, this is what it looks like really close up. You see it? And they get that spike coming up. All right, now, here's the green actually turning into, the red. Here's your muons, your neutrinos. That right there is the tau. It's got two blacks and one white. All right, the two blacks are the muon neutrinos, and the white is the electron neutrino. Then it starts to concuss, and it actually shows itself with 2 and 2, which is a photon. So you got tau, you got photon, and here, right at the venturi, you end up with your muon and electron neutrinos. They split. You see the radiation backwards? You see that? That's what's called reverse EMF, reverse electromotive force. Boom, boom, boom. There's such an explosion going on here that it's creating those kind of fields way out there. This is literally, and I'm not kidding you, literally a subatomic nuclear explosion. All right? Normally they're atomic explosions, big chunks of stuff, and they go everywhere like hand grenades. This is just splitting the photons of light and having them come right back together instantly. Fission and fusion. In the middle is raw energy, and I don't see any reason that we can't harvest that raw energy right there. Right here. Put a harvester right in here. Just like this, a solar panel basically. We have increased the value of this energetic particle. Enormous, absolutely enormous. And energy is nothing more than brilliance. The more luminosity, the more energy. That's a fact. Ask any physicist, they know that. They rate these accelerators, how explosive and how much power they're putting out by luminosity. That's it right there. See, I'm not just running my mouth. This is CERN, high luminosity LHC. High luminosity project aims to crank up the performance in order to increase the potential discoveries after 2029. We can do this today. Listen to this. Luminosity is an important indicator of the performance of an accelerator. It is proportional to the number of collisions that occur in a given amount of time. The higher the luminosity, the more data the experiments can gather to allow them to observe rare processes. Well, we're squirting them all day long in just absolute enormous quantities, and we're using light instead of protons. So we're seeing the smallest events, but we're seeing them in bucket loads. Okay, so she said we need a new model. Here it is right here. The new model is dipole electron flood theory. That means there is nothing but electrons, but they are dipoles. And the dipole electron is made of neutrinos. All right, a muon and an electron neutrino. Nothing more than a bar magnet. All right, two of these together make a photon. This has a magnetic field around only the glowy part, and it wants to burn and attach. It will create lightning, static, electricity, and it will burn into things to incorporate into it because it does not want to be alone. This has a field surrounding the entire particle, and it will bounce. It'll go boing just like that. Depends on how hard it hits and what it's hitting and the push and the shove and so forth. That's a whole nother thing. There's something called rest mass, and then there's mass in action, basically. Now, so we have an electron, which is these two, and that consists of the two neutrinos. Now, the tau, third neutrino, is this. And all that is two blacks and a white. All right? So instead, we see them coming through, they look like that. And that's all you can see. And I show it, or I will. And I don't see any reason we can't harvest energy off of that. Right here, the particles are separating, and the reverse explosiveness is absolutely stunning. They're absolutely the most luminosity you could possibly get. So if this is true, the particle physics, the way they explain gain in energy, and I believe that they may be just about right, this should be somewhere at least 200 times as powerful as it was back here. And I'm going to tell you something right now. You don't see this. But over here, there's particles all over the place. They're here too. And here they are right here. You see, all of a sudden they show up here. Well, why? Because they're being pushed back against. They're coming, but they're just, they're just sort of rambling. We see this one because it's dead in line with the Venturi. That's the only reason we see this one. These are just coming. They're just coming. That's light. That's the way light looks. You don't see it until you illuminate it. Like we illuminated this one, and that only happens when you push and shove things. The harder you push and shove against something, the more brilliant it gets. That's why the accelerators get brilliant when they smash head on, and then they can see all kinds of events. You want to see an event? I'll show you an event. All right, you saw the white spray coming out like this. That's where the Venturi is. If we were standing right here looking into the Venturi, we are completely in that white spray, which has it doesn't do anything. It's these little tiny spritzes like here. So we're in the middle of it. Surrounding it was all the black particles coming back together with these white sprays. You see them? That white spray is going to create, each one of them is creating a field, which is the Higgs fields, and that's because it's now reincorporating the white back into the black. That's what this is, and I can show you that. So we're standing here looking into this, and that white spray is coming out at us. You see this one up here? You see that? What's that doing there? You see that? You see that little trail behind it? Swishing off that way? What the hell is going on here? What's that? What is that? Well, I think I can show you what that is. It's a reverse spinning particle. They're supposed to spin to the right. I believe that is a left spinner. They're supposed to spin to the right. I believe that's a left spinner, which will bring its field into itself. If they're looking for interesting, that's pretty damn interesting to me. I believe that's that white particle, and its field is scrubbing in a reverse mode to the other one that's going this way and twisting off a little spinner. And that's it. And anytime you see white, that's energy. That's the most energy there, and of course where it's originally the head concusses. But I believe this white is because it's scrubbing against at that one spot. Now you see this? This shows the whole thing in one shot. These are the Higgs fields. These are Higgs fields. The tip of each one of these is this tip right here. The black is reincorporating into the white at this very tip, leading tip. Down here, you still have the white. It's back here. It hasn't concussed enough to start absorbing the black. That's all I can tell you from seeing this. Every tip has that black. Every now and then you see a couple in the well area, the backwards area, that have taken on the black particle. Why, I can't explain. But every now and then you do it. Maybe it's just a direct concussion. I don't know. And why are these blacks attaching way out here when they separated back here? There must be additional extra ones laying around out here so they can just bang into them and they become back to particles which have a black and a white attached to it. But this is pretty much shows the Higgs fields, the reattachment. So we got particles, we got them separated them, we got them coming back together, and we can see them half and half right there. All right, last words. These are the particles they see. They know they're there, and there's no question. These are the same particles. They say they're the tiniest ones they can see, and yes, they're coming from light. That's why they're so tiny. And yes, two of them back to back make a photon. And yes, we can separate those particles into their muon and electron showers. There's the black one, is the muon, never doesn't do anything, it just stays the same black. The electron showers get forced through this little tiny venturi that's here, a very tiny slit, which forces all the particles to crush together. And it's the same thing they do at CERN, only they go head on. We go this way. Virtually no difference. It's field to field. And making a field hit head on is very, very, very difficult. That's why they only have a few collisions. We got to just squirting them like all day long. We could squirt this just continuously all day long. And I think we can harvest that energy all day long too. And these are the particles coming back. And where do they come from? I say they must be just laying around out there waiting to come back. These particles here didn't jump over to there. We know the white is separated completely 100%. There's not a taste of white or black in here. It's just 100% white. How did they come back here? If every particle over here already had a partner, where did these come from? It appears to me that there's more blacks than there is white. And I think that might be indicated by that tau neutrino. Let me show you one more time. Okay, as I mentioned before, I think, I was always perplexed by how that black ball got so quick back to the white balls after it went through the venturi. I think there's extra black ones. They come through first with the white and two blacks, and then they show up this way. Now, these are other light particles, but they're not in direct approach to the venturi, so they don't have quite the same characteristics. But you can see they start to show up with a black, white, black, and a little tiny bit of white coming because they're starting to build up and concuss. Here they're just sort of flowing. I think that's their natural inclination, is to just spin that way, well, to go that way forward. And then this is as they are being pushed back against, because they're bouncing back and forth against this venturi. That's what's stimulating them to turn into what we see as these photons. Is a photon normally just two blacks and one white? I don't know. I don't really know. Maybe this is not even a photon. Maybe this is a double neutrino. At this point, it just dawned on me that that's possible, because until they start concussing, they won't show this way. That's what it's showing before the concussion. Is this normal? And that's concussion only? And then that's separation, which is not normal? That normally doesn't happen, I don't think. All right, a bunch of questions I've got right now. I believe these could be the neutrinos, and that supports the extra black, which is just laying around, so when they come through the Venturi and separate, they can easily find a black to reattach to. That's the only thing I can think at the moment. And it accounts for the different weights. All right, as I told you, I am a material scientist. If I can't show it, I don't talk about it. I have shown you the dipole nature of the particles and what photons look like as double dipoles, and an atom is going to be all of these particles in a ball, approximately 1835 of these particles in a ball make the hydrogen nucleus. All right, molecules are just bigger and bigger and bigger balls. But guess what? The white goes around the black. We've seen they can separate. No one's ever understood this, and I wouldn't have understood it either. I would have never suspected they could break apart like that. But it appears they can push the blacks towards the center and coat around the outside with the white. And I can show this in space, and I will in a second. So what are we saying here? We have muons, the dark matter, and that's dark matter, dark energy, and its gravity. That's what the muon. They never knew it was there. They never knew it was attached to the electron. That's why this weighs, my calculation is this weighs 0.0435 or 465, something like that. And the black weighs all the rest, almost 95% or more than 95%, according to my calculations. And then you have the muon, stays that. It never changes. There's nothing you can do to change that. Never going to change. And it wants to be attached to a white one. The white one can be this, or it can be that, or it can be anywhere in between. It's a shower. All right? Can I prove this? Can I show that this is the type of a molecule that all the white goes to the outside and the black is on the inside, and the black is the hard, heavy-duty 95% weight, and this is just a burner? Yes, I can, and I will do it right this instant. Don't forget, the electron neutrino is the light one, has almost no mass at all, and burns like hell. The muon neutrino weighs 95%, ends up being in the center of the nucleus, surrounded by the white particles, so we have never seen that dark before. All we see is things that bounce back at us. So they say, well, that's all that's there. No. Inside of it was the black particle we never saw, the black particles. And I could prove this, and I'm going to do it right now. All right, I'm going to prove to you right now that my model is correct. These are the two models. This is my model right here, where I say all the dark matter is in the center, surrounded by white particles, and these are the white particles. Now, this is a hydrogen. One more wants to get in, because the dark is so attractive, and that white will try to push its way in. But these whites, or red in this case, say, no, you can't come in. We have enough out here. We got enough. You have to stay away. And it tries to get in, and this is the quantum distance that they talk about. This is the standard model, one big, huge positive, and that's all it is a positive, nothing else, and one tiny little negative. It doesn't work. It would go, and that would be the end of it. This works flawlessly, and this is 95% of the mass, because this has no push to it. I mean, it burns, but it doesn't push anything. This pushes and doesn't burn. And I'm going to prove that in this atomic bomb blast. Very, very obvious when you see this. All right, are you ready? This is the Teapot Apple II Q House atomic bomb effects. Atom Central. Now, it was in slow motion already, and I put it down to 25% of the normal speed, so it's very slow motion. But what you're going to see is this. This is an atomic bomb. It's sitting on a tarmac here, a mile away from this house, approximately, somewhere in that area. What they do is all of that white particles are surrounding the dark matter. There it is right there. There's our dark core. There's the surrounding particles. What they do is they crush that in so hard that everything goes out. And the first thing that's going to come out is the white. And the white particles are just burners. They don't push anything. And then the next thing to follow behind it is the black particles that will be separated. And they just knock the house down. Here it goes. Now watch what happens. The first thing that's going to happen is just going to vaporize. Okay, watch. The first thing you're going to see is this. Now, I'm stopping it here. This is nothing but raw electron, white electrons, neutrinos. These are 100% electron neutrinos are in the air now. Now, they are the burners, and they're the white ones. Watch what happens. Look, it just burns the house. It burns it. It hasn't moved. Nothing has moved here. Remember this. This is of utmost importance. You see these poles, you see these wires, you see every single thing here. All the shingles, the house, are just smoking up. They didn't go anywhere. They're just barely moving. See it? Just barely moving, hardly moving. And all of a sudden, the black starts to come. Boom. No, I just stopped it. You see what happened? That's the concussion of the black following the white. And the house goes. I mean, it's not burning anymore. Everything goes. Now, watch what happens after it finishes up. It starts to come back. That'll be because there's all the blacks, are not a lot of them, but well, a lot of them will still be back there. And the whites will want to come back to the black. So everything turns around and comes backwards. Watch. See it going out? Watch. Now watch really careful. Watch it come back. Here it coming. It's coming back. Why would it do that? Watch it come back. That's how the black and the white works. The black is gravity, and the black is still back here, and it's gravity. And I think we got more black than we got whites. And that's why the Earth is filled with blacks, and the whites want to come to Earth. That's what is Earth ground. They get sucked to Earth. Let me show you what the Russians found in space. All right, let me explain it something. This is what the Russians found in space. This is in zero gravity. That's the key. And they injected charged particles. Well, let me tell you something. What's coming from our sun are charged particles. So they're coming into our atmosphere. I believe our Earth has more black particles inside, and all of these white ones are attracted to it. That's what makes them go into the Earth, and static and electricity and everything Earth ground. It wants to suck in all these white particles. All right, if you're standing out here and these white particles can get to Earth easier than going through you, you won't get electrocuted. They'll just go to ground. That's what Earth ground is all about. And we're in space just like that is. Because this is zero gravity in a vacuum chamber with charged particles. And that is exactly what our situation is. We are in space, floating in space with charged particles all around us. And I say we have more black inside attracting those white particles. I mean, that's what's happening out here. Why isn't this one for one? We know they're charged particles, but so what? Does that mean that there's more extra whites than there is black? Or are they just... You know, when they say charged, they must have more blacks than whites, or more whites than blacks, one or the other. As far as I'm concerned now, these are separate particles. The muon and the electron neutrino are separate particles. Normally they want to be glued together. But when you have an excess of one or the other, you're going to have this kind of a separation. That's my final word.